afternoon, ladies and gentlemen. My name is Vitaly Lisowski of Ukrainian team, and I'm reporting the problem number 1, thermal clock. In this problem, we asked to construct the most precise clock using periodic change in temperature, using a continuous heat supply, and the device shouldn't have any moving parts. Yes. It's outline of our report. We will start from a short problem overview, then make phenomenon analysis, then you create the clock and optimize it. So, how the precise clocks are built? All the precise clocks in the world are built on the self-oscillations. For example, my quartz clock have a quartz resonator in it, which produces 32,000 oscillations per second, and the electric circuit which counts these oscillations, and each 32,000 oscillations, it counts 1 second. In the same way, the most precise atomic clock in the world clocks. In the problem, we asked to use oscillations of temperature. So let's consider different processes which create the self-oscillatory temperature fluctuations. First of all, it's some chemical reactions, but they have broken periodicity and quickly fade. Also some connected flows, but they are slightly unpredictable. Also still homogeneous, but we must not have historical things. And we will stop on sound in resonators, because we have only 2 types of parameters to fix to make the frequency precise. It's geometry and temperature. Yes. So, how to obtain the sound under continuous heat supply? We will stop on the thermoacoustic effect. For example, when glass is blue in the bulb, he heats this part and cools down this one, and he hears the sound from this too. So we will use such setup as source of sound. We have no solid moving parts, and working substance is air. Yes. So the typical thermoacoustic tube is built in such a way. We have a test tube and a stack inside it. We are heating the left part of the test tube and cooling down the right one. We heat the left side of the stack and cool the right side of the stack. So we obtain such temperature distribution in the stack and tube. So this tube is quarter-length resonator. So sound wavelength is 4 lengths of the tube. And frequency is speed of sound divided by wavelength. Speed of sound itself depends on the temperature. So frequency will depend on the temperature. Next slide. So on this video, you hear how the simple thermoacoustic tube works. Resistor is a heater. You could also see it's our stack. So frequency is stable enough, but a lot of periods of time it changes. Let's try to explain from theoretical point of view how this tube works. So let's consider the portion of air moving from the open end towards closed end. It heats and also it compresses. So after such pressure, it wants to go back, and it cools and expands, reaching the end of the tube, the open end. It reflects from the atmosphere, and the process continues. Thus, the temperature of air portion in the tube varies periodically. Let's talk about our stack. The first role is to maintain the necessary temperature gradient between the very hot part of the tube and very cold part. Also, it must provide efficient heating of air moving towards the closed end and efficient cooling of air moving towards the open end. We must provide this with frequency of 500 Hz, some frequency, so for each 1 millisecond. Next slide. From the theoretical point of view, the depth on which we can heat the air using such frequency is called the thermal penetration depth. So we must have a pore size in our wool of about penetration depth. For our frequency is something like 0.1 millimeter. It's the next slide. Also, we tried to study the optimal stack position. Both from theoretical and experimental point of view, we discovered that the central part of tube is the most optimal stack position. Next slide. Also, as you understand, we must maintain the temperature gradient across the stack, because one part of it must heat air and another part must cool it. So on this photo, you can see the stack and the air. This part was heating air, and it is covered by oxide tint, and its color shows the temperatures at which it was. The left side was cold, so it has a metal color. The temperature gradient in the stack must be larger than the critical gradient to produce acoustic oscillations. On this slide, we discuss the gradient of temperature across the tube itself. So we took a thermal camera and looked at our resistor. It was very hot and the tube was very cold. But then we took a tube out of resistor and really this part was very hot and this part is very cold. And it's modeling of our system in consolidated physics. Next slide. So we now want to create a clock. For this purpose we need to know which parameters affect frequency stability. When we make a stable frequency, we obtain a clock. So we have geometric parameters such as stability of geometry of tube, position of steel wool and so on, and temperature parameters like temperature stability of heater, cooler, and also room temperature. Next slide. Geometrical parameters are very easy to fix. We must use tubes made of quartz glass because it has very low thermal expansion coefficient and very high molecular temperature. Also, temperature of resistor can be easily fixed by using a thermoregulating circuit. Coolant temperature can be kept constant using a constant water supply. But some other parameters like room temperature and so on can be fixed so easy. So we decided to put two tubes into one room. Two tubes with almost the same frequency in almost the same conditions, and they would have almost the same frequencies as I told. And we don't look on this frequency, but we look on the bit frequency between them. And the bit frequency remains almost constant after changing any conditions. Next slide. So in this video, you heard the beat. And this is our first clock. It's MATLAB code which is counting our clock, it's machine clock, and it's a difference. So we can estimate the error. On this screen you see that frequencies are very stable, the frequencies of two tubes, this one and this one. And we obtain the error 1 second in 1 minute. Why? The question is, what's the main reason for this error? And we discovered the main reason was incorrect determination of frequency by us ourselves. So to make this code working correctly, we must put the correct frequency. But for example, if the frequency of bit is 10.01 Hz, but we put 10.0, we have such an error. So the problem is, but such low frequencies like 0.01 Hz is not too easy to measure. So we must know how to tune frequency of tube to make it exactly 10 Hz. The simplest way to do it is to put a metal rod in the tube and very slowly move it. Moving it, we can slightly vary frequency. So, next slide. On this photo, you can see this metal rod and this test tube, also a cooling system and so on. And in the left corner, you can see our clock. I took photo at the moment when we had achieved the error of 1 second. It was at 16th minute, so 15 minutes our clock worked precisely. So as you can understand, this error is rounded, so we had error less than 1 second, and at 16 minutes we obtained the error of 1 second, and so on, 2 minutes, 2 seconds, yes, that's right. Until this point, we were using computer as our card. It's not the best idea, because computer has a timer itself, for processing sound and so on. So using timer to create a timer, it's a bad idea. So we decided to make a small good counter. We simply took a calculator. By pressing on the equality button, we can count the number of pressures. So we attach 2 wires to the equality button, and shortening these wires, it's the same as pushing this button. Then we can type, for example, if we, here we have microphone and amplifier and transistor. When we have signal on the microphone, the transistor is open, so this button is short. For example, when we have frequency of 10 Hz, we can simply write something like O plus 0.1 equals, and then turn on our screen. Why? Because each oscillation is 0.1 second, and such you can calculate each second. Next. On this video you can see how the calculator works as a counter, and it's very much image, and this is machine clock. Also, so it's microphone, it's our circuit, and it's calculator, and the other system is the same as on the previous slides. Let's discuss the full experimental setup. It's what a full experimental setup. It's a power supply for our heating resistors. It's our test tubes put into heating resistors, and also it's glass, which is condensator of water, and it's a water supply which flows from up on this glass. It's metal rod, which leads to very frequency. It's our accounting device, this power supply. Probably I missed the computer. Computer is simply to monitor the frequency is really stable. The next slide. So it was the final version of our clock, and now we would like to discuss how can we improve it if we had enough money. So, first of all, we would like to create the thermal stabilization of each element of our device. So, thermal stabilization of cooler, heater, and so on. Also, our device is extremely noisy, so we would like to make an acoustic insulation around it. The next slide. Also, I did not mention that we can also use sleep seconds. For example, if we know that systematic of our device is 1 second per 100 seconds, we can each 100 seconds add 1 second. So, current system. So, conclusions. We have created a thermoacoustic source of sound with specified frequency, stabilized this frequency, and based on this frequency, we created a clock. Our clock was running with a row of 1 second per 15 minutes. It had no moving solid parts. It has a continuous heat supply, used in oscillations of temperature of A, S, and time. So, thank you for your attention.
Thank you very much for your presentation. Now it's time for the opponent to ask questions.
So if I understand your definition of the precision, what is the definition of the precision?
So we have our clock, machine clock, so correct one. So we have some kind of this and sometimes this. And the difference on these values divided by this value is our precision percent.
Okay. How does the precision varies? What are the parameters that influence the precision of the printer?
Okay.
In which way is the printer involved as an influence on the precision?
Okay, thank you. The main parameter influencing the precision is the precision of determining all parameters of our setup. The main is frequency of bit. So if we know frequency of bit with high precision, we can make a program on our calculator or computer which counts time with high precision. Of course, the calculator itself has some precision, so it also affects. Also, some stochastic parameters which we can't take into account may be important.
Okay. What is it? So for which typical measure duration would your clock will be useful?
So can you repeat?
For which measure duration will your clock be useful?
Can I call the insulation?
The duration.
Duration.
Next. Stable for this duration, I'll call it stable, yes?
Yes. Okay.
Okay. So in our experiment.
Time is up. Please answer the question. Please answer the question.
Okay. So in our experiment, we achieved precision 1 second per 15 minutes, and I think we can really achieve precision much better.
Okay.
Okay, thank you very much. Now it's time for preparation of the opponent's speech. Okay, so time is.
So first of all, thank you for this very nice presentation. So I noticed that the very positive point is that you have built a very nice setup, and you have a really interesting idea using a thermodynamical device to answer the problem. Another serious positive point is that you build not only a metronome that beats at a certain frequency, but you also have built a printer that actually give us the result of the measure, that you really did it experimentally. Moreover, you explained with very much detail the physical principle behind your setup and why it actually works. You studied empirically the optimization of several parameters, such as the stack position, and you have studied how the other main parameters could have an influence on the precision, such as temperature gradient. But I think that we would have needs an explanation on the principle behind the precision of a clock. For instance, how the frequency of your device have an influence on your precision. If it's better to have a device with a very high frequency, and maybe you could have said at least theoretically what would be the better frequency. Moreover, about the optimization. So yes, you haven't spoken about the optimal frequency that your device should have, and you also have not talked about what is the typical duration on which your device is the most precise. And moreover, I think it is that in the theory, it would need a kind of more theoretical explanations on the theoretical relation between the precision. I would have liked a theoretical definition of the precision, and then to study the dependencies of the precision with the frequency of your setup, and you could have deduced for which duration would your clock be useful. And also, one of your strengths was to have built the control, but maybe it's me because the presentation was very fast. I don't think you have stated what are the principles that causes the imprecision in the control, and how, at least theoretically, you could have acted on the control to improve the imprecision linked with the control. But I think you made a slide on it, but I'm not sure I've understood it. So what I'd like to talk about is first, in your experiments, so what is the principle causing the uncertainty in the control and how to improve your setup? And the same for the tubes. So what in the tubes is the principle causing variations of the frequency, and how to improve it experimentally. And in the second part, maybe we'd like to talk together of what to study theoretically. What would have been a better for instance, what is the link between the precisions and the frequency of your device, and the link between the precision and the duration that you measure, for instance. So my first questions, maybe I'd like to talk about the control.
Thank you. Really very good questions about precision, but you had one question not about precision. You told there that I didn't measure temperature. It's not correct, because I had a photo with a thermal camera where you can see the temperature of each part of our setup.
Yes,
how it was.
You did.
Yeah.
You're right.
Okay. So the talk about precision. You started from the question about the very high frequency. The problem is my calculator, this one, I can show it. It can't calculate impulses very fast. So it has some, for example, I can't calculate impulses of pulses or of frequency even 20 Hz. So 10 is okay, but 20 is not okay. So it has, it is not very good reference from this point.
So you think it would be better if you have a higher frequency for the precision?
From the one hand, yes, because if I have a frequency of 1 Hz and due to some unknown reasons I obtain something like 1.001, it would be a large error on large current. And if I have frequency of 10.001, sorry, frequency of 10, and due to some reasons such error, it's much better because
So maybe you think that what's important, I think that what's important is actually the imprecision of your frequency relatively to the frequency itself. So maybe it would have been interesting to study the ratio of the uncertainty of your frequency divided by the frequency itself, because it's the important parameter that have an impact on the precision.
I've proved experimentally that we have much worse situation than using so low frequency. I tried to make a block based on 1 Hz frequency, and here it was not precise. I don't know why, but frequency was really drifting so from 0.9 to 1.1 and so on. And when I had 10 Hz, it was okay. So we had very precise clock, and really you see that 15 minutes is okay.
That is really 10 Hz is the frequency of your sound?
Of our beat. So we have two tubes. This one is in different experiments we use different tubes, but for example this one is shown here. It's something like 685 and 695.
Okay.
So and beat frequency is 10. Okay.
Okay, I think
so this difference is actually
used this frequency. Okay.
Yeah.
So why not have used this frequency which are higher?
Okay.
So it's because, if I understood, it's because of the limits, technical limits.
It's the first reason. The first reason is really hard to calculate such high frequencies. But the second reason is precision, because when we have one tube and any change of outside parameters will change its frequency. Okay? And if we have two tubes, all these parameters will change when changing outside parameters. And if this difference is very low, we have the high precision.
So maybe I think that there are several phenomena that are involved on the precision, but maybe it would have been interesting to study first to introduce for which duration your clock is useful. For instance, indeed, maybe it's better to have a lower frequency for higher measure of duration, and maybe to compare the influence and on which period of time is the variation of outside parameter, and compared to the actual durations that you want to measure.
So I don't pretend that my clock is the most precise in the world, and so on, but I really believe that the parameters which can influence the stability, I don't know, it's geometry, but we can know most of problems using these quartz tubes. So I know this, and the main left temperature. So temperature, we have cooler here, we have heater here. So each of them must be stabilized, and to show the last slide, the very last one with our proposal. We really propose not to keep on, not to like the thermal stabilization of resistor itself, but really create a very good thermal stabilization system, as for cooler, as for heat. In this case, we can obtain really very precise clock, extremely precise clock, because nothing will affect it.
So actually, with this setup, you try to maintain the mean frequency of your setup constant all the time?
Yeah, exactly. So I have.
So you're talking about...
Excuse me, the time is out. Now is the time for the questions from the reviewer.
Yeah. So I believe you talked a little bit about the thermal penetration depth. Can you maybe show me that slide? And tell me how large it is?
It's 0.1 millimeter. Let me explain. So, thermal penetration depth, it's depth of air. So we have a metal plate and air. So it's depth of air on which we can heat when heating this such liquid, so during such time. Okay.
So this is where you have the length scale over which you have the large temperature variation or what? Yeah. Or have I understood it correctly?
So this formula gives us the necessary size of pores of our stack. Stack is porous media, and in this media we have both metal vise and air between them. So if distance between metal vise is comparable with the thermal penetration depth, that means that we can heat and cool our air sufficiently efficiently.
I don't remember. Did you talk about using a setup with a bypass loop or something like that? Would that improve anything? If you put like a bypass loop on the end of it, okay. I don't know. That was just a minor technical point, so I think I'll skip that. Yeah, I think that's it from me for now. Thanks.
Time for presentation.
Yeah. So I'm Frank Hansen, and I'll be reviewing the presentation of the thermal clock by the Ukrainian team. So first of all, I think it's obvious that the reporter has constructed a very precise clock, and the videos he showed are very nice, demonstrating that he has done a lot of work to optimize his setup. The feature with the calculator, I believe, is particularly a nice touch, because that means that he really has a clock. It's a very innovative way to solving the problem, and he mentions the heat penetration depth, and he seems to generally have a good physical explanation of the phenomenon. So some of the bad point is when a little bit fast through the theory, it's a little hard to understand sometimes, but I mean, this is really a very minor detail I'd like to stress. I didn't see any comparison between the theory and the experiment. I mean, you talked a bit about the theory of the resonator tube, which is a good, but what's actually the theory of the thermal phenomenon we were talking about here? I mean, that should be matched to the resonance frequency of the tube, if I'm not mistaken. And yeah, how does the theory make predictions about this? Then you talked a little bit about the error. You said that you had an error of 1 second and 15 minutes, and you talked about the difficulty of determining the beat frequency and stuff like that, which was something that was discussed at length. But I'd like to know a little bit about the stochastic error in some of the other things, because I mean, you talk about implementing leap seconds, but that would really require the error in your measured frequency to be very constant, and does that change with time in some stochastic way, perhaps? For Lukonen, he asked a lot of questions about the precision, asked about how to optimize the setup. Went a lot into the uncertainty, and he pointed out that there was no measurement of the temperature. But I think there were a few points that could perhaps have been brought up. So for some of the discussion questions, which I would like to ask both the opponent and the reviewer, does water cooling temperature, I mean, if that changes, does that create a drift in the system? What about the environmental conditions? I mean, you talk about the beat frequency to stabilize that, but is Is that really so constant? Yeah.
Time
And
is
yeah,
over.
that's it from me.
Let's start with the discussion between the reporter, reviewer, and opponent.
Okay, so thank you very much. Again, very good questions. You started from the seconds. Probably I had no time to explain more detailedly. It's a very simple way to avoid some systematical errors. For example, if we have our clock, and machine clock, and we know that, for example, here we have 100 seconds, or 1000 for example, and here 1001. And we made this experiment 5 times and ensured that this difference is always the same. So we can easily put in our calculator, our code calculator, making +1 at each 1000 seconds.
Yeah. But that really assumes the stochastic error to be very small if you have to do this right.
Okay, so I think this procedure is, so we really try to do this, but okay, in the final setup we do not use the leap second.
Okay, I'd like to hear what the opponent thinks about this point.
So about the water, is the water?
No, just about
the derivative or the stochastic?
yeah, something about the precision. I mean, how do you think that it will change with time or stuff like that?
So first thing I like saying that if the imprecision is due to stochastic effects, the longer the duration, we measure the durations, the better the precision will be, and that if it's due to the drift, the shorter is the measured duration, the more precise it will be. So actually it would have been interesting to see that there is an optimum between these two parameters. So to answer your question, I think that if you use a frequency of 10 Hertz, it's it's not very as the inverse of 10 is not very big in front of 1 or 10 minutes. Maybe that's what is the typical duration? 10 minutes. It's not very big. It can be due to the stochastic effects.
Also, I think I'd like to. Just talk a little bit about the environmental conditions. I mean, you've used this to improve it, right? But have you checked how constant it remains?
Yes. So we thought that our thermostabilizing system is okay, but primarily based on the experimental observations. So we know that our clock really is precise value. It's experimental observation. We try to work under such temperatures as far as I remember, something like 14 degrees, 16, and 24, and the clock was going okay at all conditions. So I think that it's enough proof to tell that my approach is good. Yeah.
So you keep talking about the precision of your device, but actually, if you must maybe you must consider or state before that what is the typical duration for which you want your device to be precise, because the precision depends on the durations that you want to measure. So, for instance, maybe you said that.
Okay, now we start general discussion. Please continue.
So we used the two tubes to have a lower frequency, just in order to compensate the effect due to the drift. But maybe if you wanted to measure a very short period, such as just of 1 second, you could have used just this device with its imperfection about the drift and be more precise relatively to the duration because you have a higher frequency.
Okay, so I took what you want to say. So again, the tube was. Can you show the first abstract? Okay, so we used different tubes and found the best one. You can see here, it's 4 different tubes shown here, but here we used something like 6 different tubes of different lengths. And generally, this was the best one for several points. First of all, it's the point of how easy it to obtain some acoustic oscillations in this tube, because at some tube lengths it was necessary a larger heat supply, so it's not energetically okay.
Okay, Timo France.
I have a question.
Yeah.
Did you calculate the frequencies you obtained from the tube?
Selected, yes.
Did you calculate them? Okay, and did you use the Navier-Stokes equation, since there is a...
Which equation?
Navier-Stokes equation?
So no, I do not use Navier-Stokes equation. These frequencies which I write here, it's measured, but you can show the formula. It's a formula on the first slide. Okay, this is this one. So you understand that frequency is the speed of sound on this one divided by 4 lengths of tube. Okay. So we can calculate the frequency for our temperature, for our two temperatures, to be more precise, and to compare that it's really true. Yeah.
It's a little bit of continuation. So do you have any comparison between?
Okay, yes, I have no some numbers here, but maybe I can give you numbers. For example, we have test tube, and here on the left part, its temperature is something like 800 degrees. You can see it's on the thermal camera. And here, I can see it's set, and here something like 27. Okay. And then you calculate the...
I'm sorry to ask, but do you have you theoretically estimated how precise your clock is? Have you been able to? Through your theory, can you say, you don't have a comparison between your theory and your experiments?
I know that you should. I know that my theory, I compared it, and I know it is correct. So
but you show us that it's correct. You're saying you know it's correct, but...
You can calculate it. It and calculate.
Can I help the reporter? It relates.
This is a general discussion. You can.
Yeah, so our answer is that we have theoretically calculated the frequencies for the tubes, we have compared them with the measured frequencies, and the comparison is suitable for our purpose.
But
And we have the numbers.
So could you show us that?
We have the numbers to prove it, but we have measured, we just don't have it on the slide. The numbers,
Okay, I think we would have liked to see a bit of the theoretical comparison, but I mean,
so we have we have theoretical comparison in different parts of the presentation. For example, right here, or even on that slide, we have a theoretical prediction for the optimal position of the stack, and then we
it would have been nice. Sorry. It would have been nice if it had been shown. I think that was the only point. And I'm sorry for all the aggressive tensions stuff and that.
I think if you heard any difference, I will show it, but we obtain the close numbers, so I said it is not interesting.
Timo France.
I want to put another point, which is you talked about the precision of the contour. There was discussion about this. And so, what do you think about the influence of the electronic noise, and how can we improve it? Question for both of you.
Looking at this electric circuit, we have done some work when building this circuit, because we had to choose the resistors luminaires to make the amplifier coefficient from our microphone such so we can have threshold signal. So we have something like that from the microphone, for example, and we make some threshold with this, for example, level, and count on the peaks.
Okay, can you briefly finalize?
Yes, to finalize, the precision of our counter is precision as number of digits of the calculator. Okay, so each can has only 10 digits, and it's not.
Okay, so now it's time for concluding remarks of the report.
Okay, so I'm really glad to hear some interesting questions about precision and so on. And I think that my solution is good, and it's very good if I I could realize the setup, to create the setup shown on this slide. Because I think it would be a very precise log shown here. Thank you.
Okay, thank you for the presentation. And it's now time for questions of the jury.
I managed without microphone. You put temperature in your formula for the speed of sound. Which one of the, because at least there are two.
So we really make a model, when we have a tube, we can make different models. For example, the simplest one is we have simply a tube with one temperature and then another temperature, and calculate efficient length of tube or efficient temperature. And we also can take into account the stack. And temperature gradient in the stack is something like that, and then the same. This model gives a more precise value, but similar in independence. But really, I think we must calculate in such a way.
But which one is here in this formula?
The effective one.
I have a question for all the members. What do you think if the effect, Joule-Thomson effect of jostling the gas over the core structure is important for understanding the physics of the process? And what's the temperature conversion for this?
I want to tell you slightly more about physics of this process. So really, in this point, the physics of the stack is, it has two main parameters, to create the temperature gradient and to maintain and to heat and cool down air. And really, I have never heard in any articles or something like that mention of Joule-Thomson effect. I really think we can take it into account if we had really very little core size, even more.
I'm not sure I understand the question. It is, what is the influence of the porosity of the stack? That's it?
Or the Joule-Thomson effect. Or the Joule-Thomson effect.
The Joule-Thomson, it's the name of the decompression, I think? That's it.
No, it's an effect when the gas is going through the porous surface.
So, and what is the influence of the porosity? Okay, I think.
Okay, let's move further. So just we have more time to answer.
So, the more porous the stack is, the more true will be the more reversible will be the depressurization.
Okay, could you please be a bit more quicker, because we have a lot of questions here.
Okay, so we will be more precise if the stack is less porous.
Yeah, I mean, I didn't construct the thermocloud in this way, so I haven't really assessed the way the Joule-Thomson effect influences this.
Okay, thank you. Now I have a question. The first question is to the reporter. Is on your ultimate video the clock with the best precision?
Yeah.
Will you show me to me, please?
Okay.
Yes, last video with.
I'm not sure about last video. It's I think yes, but I'm not sure.
Okay.
Should I show?
Yes, last video. And the end of this video.
Yeah, I understand about what do you talk. The reason is that calculator vehicles have some time after they turn off.
No, I said that I say about the video where time is 14. Yes. Okay, the end of the video. Yes.
Okay. Yeah.
Is there? Yes. You can start.
So I can't insist on its really good example.
Okay, I'm sorry. And you will stop when the number will stop. I think it will be 5 seconds. Why so? Okay, it's okay. What is the relative precision of this number?
Okay, so now you see something like 11.3 and 11.04, yeah?
Yes.
So I think yes, it's really not very good examples.
Okay, the question was about the precision.
Sorry, how to remember?
The right side, you see frames, and in each 24 frames,
It's number of frames. It's not milliseconds. It's number of frames.
It's the frames, and each frames of 4 frames
Do you have 100 frames per second?
24.
Well, that's not the case of this. Okay, and may I ask another question? Was it very difficult to plot a simple dependency of frequency of your experimental device on time? And why didn't you do this?
What's the backup slides?
I was a little bit confused by some of the discussions before, so we have that thought for Vladimir. Whenever I make a measurement, I have to consider 2 different types of error, which I usually classify into accuracy and precision.
Okay.
So what would you say is the accuracy of your clock, and what is the precision?
So by the accuracy you mean
I mean accuracy.
Okay, so I understand the difference. You want to divide my errors into errors of my system of measurements and into errors of compounds of my system, or something like that, or my error of my methodics and error of my compounds. So I think methodics is good, but we're really not sure that we can take into account all stochastic effects and something like that. So I think it's the reason why I can't answer very good on your question. You can't take into account all stochastic errors.
Why the peak frequency was more stable than the frequency generated in the tubes?
Okay, very good question, thank you. So first of all, it's experimental observation, it's low. Then, from the theoretical point of view, on the so you have frequency is proportional to the square root of the temperature. When temperature is changing, the frequency is also changing. But when we have 2 different frequencies, its difference has a lower change. Okay. So if the 2 frequencies are very close, the change is extremely little.
Extremely short question.
Can you shortly and clearly state what are the errors in your system? Do they come from statistics or do they come from the offset?
Okay, so I do not know which errors can come from statistics, but I guess I have so, probably have so. And errors from my setup is simply the stability of temperatures of my system.
Okay, thank you very much. Now it's time for jury members to decide the marks. Now we are grading the reviewer. So 7, 9, 8, 7, 8, 9, 8, 8, 9, 7, 9, 8, 8, 8, 8, 9, 7, 7, 8, 8, 8, 8. For the opponent, seven, 8, 7, 7, 7, 8, 8, 6, 7, 7, 7, 7, 7, 7, 7, 6, 7, 8, 7, 8, 7, 7. And for the reporter, 9, 9, 8, 7, 8, 9, 9, 10, 9, 8, 8, 9, 8, 9, 6, 7, 8, 9, 9, 9, 8, 7. Okay. Concluding remarks of the jury members.
I think my marks for the reporter and the opening were the lowest. And I want to say that it's strange that you never heard about Joule-Thomson effect, as it's one of the well-known methods to obtain the liquid gases. And but I believe that really in this problem, this effect doesn't really matters, as it is proportional to delta T, which is small in this setup. But it's of course it was necessary to mention it. Also about the reporter, the only plot you showed us. The only plot you showed us isn't really necessary to investigate, but the second plot was shown only in the end of the on the fight. But why didn't you show it during your report? And why didn't you show the plot for the stability of beat frequency? That's about minuses. And I'd like to appreciate the great engineering work in your report, and the measuring of beats, but not the frequency. I think it's a great idea. Thank you.
I have given the lowest mark to the opponent team. I think it's because the things on which the discussion was concentrated was not the most important ones between in the problem solution. Because the main problem of the report is that the clock precision is not analyzed well. Even if there is no theory, but a simple experiment could be made by plotting the frequency of this 10 Hz versus the time. And it would be enough for obtaining the clock precision and how does this clock drift on time. But this wasn't made, and you should mention it. And I think that the review team has done has helped you much with your work, and because of it, a part of your points were given to the review team. Okay.
I have quite well estimate for presenter because I think that your solutions is quite original, and you use some interesting physical idea for your solution. If what we say about accuracy of your clocks, I think that it's your device is clock, but it's possible that it's need to investigate more carefully your precision, how it was mentioned by my colleagues, but I think that it's not so important that your clocks not do accuracy, that you don't investigate your accuracy in such details. The main for me is that it's quite interesting your physical idea, and in general your clocks
works.
Okay, do we have any other remarks? If not, I will invite you to half an hour coffee break.